Hello everyone. During the past two lectures, we learned a few techniques how to calculate equivalent resistors, and specifically we calculated equivalent resistors for a certain type of connection, which we call the series connection, where the current that is we're passing through one resistor would be the same as the current that is passing through the next if the two are in series to each other. And then we also did the same thing, calculated equivalent resistance, and basically analyzed the circuit for a situation where the resistors were set to be in parallel to each other, and that situation was defined as when the two resistors share the same node on both terminals. In other words, they share the same voltage across them. So in this case, the series situation, the resistors share the same exact current. In this parallel situation, they share the same exact voltage. And this duality between how in one situation you get a statement about the voltage or about the current, and the other in case you get a statement about the voltage, this duality plays an important role in a lot of analysis that we're going to do from now on. So notice this duality and how it plays really analogous going from one kind of connection to the other kind. So I'm going to quickly review what we learned, reinforce that, and then we move on and try to use what we learned to do more complicated calculation for more complicated network of resistors connected to each other. So we looked at the situation, and then we defined the equivalent resistance, which is a completely universal definition, and basically it's the definition of resistance. We said if we have a box with a bunch of components, and in this case the components are in series to each other, but generally speaking with two terminals coming off of it, if I connect a voltage across those two terminals and then look at the current that is going into that, assuming that that's the only source of energy that I connect to that box, then the result would be the equivalent resistance of that box. So in the case of the three resistors in series to each other, we did the calculation. How did we do that? We just used the same algorithm that I keep putting on the corner of this place so that we never forget our approach to any problem in electronics and electrical engineering wouldn't change. So we did the calculation. We figured out that when you calculate Vs divided by Is, you get the value that is equal to the resistance of each individual resistors added to each other. And then we also could calculate the voltages at all nodes, obviously, once we're done analyzing the circuit. So the voltage on that node came out to be R3 over all three of the resistors in series to each other times the voltage. V2 would be R2 plus R3 over all three resistors in series to each other times the voltage across the whole thing. And this actually, these equations have a name, and they're useful if you're using shortcuts later on. It's as it appears, the voltage across this whole thing, it appears that as you go from the bottom, which in this case we actually designated a 0 volt to it, the voltage obviously increases because we know on the other end the voltage is much higher than the voltage on the bottom. It's higher than the voltage on the top. So as you move up, the voltage increases and reaches the highest value that is on top. But also because the equation that defines the voltage to current relationship for these three components are linear equations, the Ohm law, the voltage linearly increases proportional to the resistance that we're passing as we're moving up. You can think of it like a ladder in energy, so or potential for that matter. As you go up this ladder and go from the 0 level potential all the way to highest potential on the other end, as you go up, the potential linearly increases as a function of how much resistance you have And again, this is a result of the analysis that we did. This is quite useful. Just notice, if you want this voltage, you can quickly say how much resistance did I move from down here, did I have to pass moving from down here to this point, divided by the whole resistance, and that would be the voltage of that point with respect to your ground. Moving up, voltage on that point would be all of the resistance added to each other, so R2 plus R3, then divided by the whole thing, multiplied by the Vs. And you can just repeat that for any number of resistors for that matter. There's another way of explaining this. You can define voltage as the potential difference across each component. And if you do that, and you call that VR1, VR2, and VR3, which basically the way that we're defining them is that, for example, VR1 is Vs in this circuit minus V2. And if you do that calculation, you figure out that it's equal to R1 over R equivalent Vs. And you can repeat the same thing and say VR2 is equal to V2 minus V3. It's equal to R2 over R equivalent Vs. And finally VR3 is V3 minus 0, and that's equal to R3 divided by R equivalent Vs. So again, if we define the voltage as the difference between the potential on the two sides of the resistor, that voltage is the whole voltage distributed amongst all these individual resistors proportional to the value of the resistor with respect to the total thing, as you can see here. So the voltage across R1 is R1 over the whole thing times the whole voltage, proportionally getting distributed between all the resistors. Now, if I give you an example of this is, say, 6 volts, and you have 1 kilo ohm resistor here, 2 kilo ohm resistor here, and a 3 kilo ohm resistor here. The voltage here would be 1 volt. The voltage here would be 3 volts, and the voltage of the whole thing obviously would be 6 volts, right? So let me just do that so that we get used to using numbers. So if this is 1 kilo ohm, that's 2 kilo ohm, and that's 3 kilo ohm, and this whole thing is 6 volts. So V3 would be 1 over 6 times 6. That would be 1 at V3, right? So at that point, V3 is 1 volt. Then you move up to V2, that would be 1 plus 2 over 6 times 6, which is 1 over 1 plus 2 is 3, sorry. So 1 plus 2, 3 over 6 times 6, that would be half of the whole voltage. So that would be 3 volts. And then finally on top you have obviously Vs at that node, right? And then if you look at each voltage, VR1 would be 3 divided by 6 times 6, that's 2 volts. VR2 is 2 divided by 6 times 6. That would be, this is, VR1 is 3 divided by 6 times 6 is 3 volts. VR2 is 2 divided by 6 times 6. That would be 2 volts. And finally, VR3 is 1 divided by 6 by. So if you notice the voltage difference across each one, when you add them up, ends up being 6. Obviously, it's going to add up being the total voltage difference across the whole thing. But also, the value of the voltage across each one is basically proportional to the value of the resistor over the total resistance multiplied by the whole potential across. Now, notice I really want to put a lot of emphasis here because this is a source of a lot of confusion. Notice that V3, the voltage on one end of the resistor R3, is different than VR3, which is defined as the potential difference, right? In this specific case, these two happen to be the same, meaning that in this special case, VR3 and V3 happen to be equal to each other because one side of that resistor is actually 0 volts. So the potential difference and the potential of that node happen to be the same. But if you move on to the next resistor, that's actually not the case. Notice that V2, the voltage on one end, is actually 2 volts. V3, the voltage on the other end, is 1 volt. But the voltage difference, which is V2 minus V3, we calculate that to be 2 volts. So V2 is 3 volts, but VR2 is 2 volts. So the voltage on one end is not the same as the voltage across that component. The potential of that node is different than the voltage across the resistor R2. This is a point of confusion and stays with a lot of us electrical engineers all the way to the end. So pay attention and try to make sense of this concept right here. There is obviously, we have discussed this already. There's a difference between the potential of a node and the potential difference across 2 nodes. And that's a really important differentiation that you same for here. So the voltage on top of this resistor R1 is 6 volts with respect to that ground. But the potential difference, or VR1, is only 3 volts. Right? Okay, so now that we are done with this, there's this equivalency for the case where the resistors are in parallel, analogy, not equivalency, for the case where the resistors are in parallel. Again, we define the equivalent resistance as being the voltage that we apply across the box, assuming that's the only source of energy that is connected to the box, divided by the current that is going into that. And for the case of when the resistors are in parallel to each other, there's a certain notation that is common where you put these 2 parallel lines to say that each one of these components are in parallel with the other one. Keep in mind, and I discussed this, this doesn't mean that they have to be geometrically in parallel to each other. All it means is that they share the same nodes on top and the bottom of the component. So this could stand like that or any other way, as long as the nodes are shared by both on the 2 sides, they're in parallel to each other. Now, we did the calculation, again, using the same algorithm, and we calculated the equivalent resistance, and in this case, it was the inverse of each resistor added up by each other, and then the whole thing inversed, and that would be the equivalent resistance. Now, obviously, the voltage across each one of these resistors is going to be the same as the voltage that you connected. That's by definition how you put the components in parallel to each other. Now, notice the analogy, how basically the duality between what happens to current in this case and what happens to the voltage in this case. In this case, the current is the same for all the components, but the voltage is different. In this case, the voltage is the same for all 3 components, but the current is different. So you switch the place between the current and voltage, you move from one situation to the other. So there's a duality between the 2. Whatever that is true about, in terms of statements that make it, that is true about the current here, is true about the voltage here. So you say the same current passing through the components here. On the other hand, here you say the same voltage is applied to all the components in this case. So you see the duality. Now, when it comes to the current, obviously the current is different with each one. Could you do that? Just the same thing. This is a result of KCL. IS gets distributed between 3. So if this is a node, basically, IS goes in, and I1, I2, and I3 all leave that node. So IS is equal to I1, I2, and I3. Now, what kind of ratio do you get between the 2? I1 is equal to equivalent resistance over the resistance that you're trying to calculate the current for times IS. Now, look at what happened here. Again, look at this duality. Here, just replace the place for current and voltage and inverse the equations, and you kind of see how things are similar or not similar to each other. I mean, the same for this one. See, our equivalent here was just the resistors added to each other. In this case, it was inverse of the resistors added to each other and then inversed again. In other words, maybe this is a better way to say it. I could say that the inverse of the equivalent resistance is equal to, this is a better way of noting this duality. So the inverse of R equivalent is equal to the inverse of each resistor added to each other. I'm just doing this to kind of show you the duality between the two situations. Here, the resistors themselves are added to each other. In the case of the components in parallel to each other, the inverse of the resistance is added to each other. By the way, the inverse of resistance, because it's used quite often, has a name. It's called the conductance. So inverse of the resistance is called conductance. So again, duality. Here, the resistors are added to each other. In the case of the components in parallel to each other, the conductance is added to each other. Okay. In the case of components in series to each other, the voltage across each component is basically proportional to the resistance of the component over the total resistance times the total voltage. In this case, the current of each component is going to be have a ratio between the value of the resistance and the total current that is passing through it. So again, look at here. If I rewrite that so that everything is a function of conductance. Now, I'm going to redo it down here. I'm going to redo it here. So I can say I1 is equal to 1 over R1 over 1 over R equivalent IS, right? Which is I1 is equal to, I'm going to call it G1 over G equivalent IS. So replace the voltage with current. Well, current of each component here, analogy voltage of each component there. For the series case was the ratio between the resistance of the component over the total resistance or equivalent resistance times the total voltage applied. In this case, the current is equal to the ratio of the conductance of the component over the total conductance, okay, total equivalent conductance times the current. So there's this nice duality, and you can take advantage of that to do shortcuts. So let's work with numbers, for example. So if I have, I don't know, if let's say this is 2K, and that's 4K, and that's 4K, right? So when you calculate the equivalency, 4 in parallel with 4 is going to be 2. 2 in parallel with 2 would be 1K. So that's 1K. Now, how does the current then gets divided, given there's a certain current passing? So you come here, this is 1K, and R1 is 2. So 1/2 of the total current is going to go through this one. You come here, and you say, again, R equivalent, we said, is 1K and 4K, so 1/4 of the total current is going to pass through this one, and then 1/4 of the current is going to pass through this one. So 1/2, 1/4, 1/4, you add it up, you get IS. Think about this duality. Think about the difference between the voltage across a component and voltage of each end node on the two terminals of the component and what that means. These are important for you to get comfortable with the kind of quick calculations that we may end up doing in the later lectures. To put you at ease, if you're not comfortable doing any shortcuts, be confident that you can always go back to our simple algorithm. It's going to take more time to do that, but you can definitely be rest assured that you're going to get the result that you're looking for. With that, I'm going to stop and then continue with actual examples when we're going to start using this. One last thing, obviously you can extend the result of these two situations to any number of resistors in parallel or any number of any number of resistors in parallel, any number of resistors in series. Thank you very much.